Right. So to ensure that process is done, everything is come to sitting gills. Now there are other bodies, but not as well known as sitting gills, and not probably as worldwide as sitting gills. Okay. Right, let's get started. Right, Magnetism 2, Session 8. To gain a fully understanding of current carrying conductors, and to look and see how the magnetic field affects conductors when it's passing a current. Right, you've seen this already, okay? Right, and this is just again a review telling you what we have done already. So look back at those videos for yourselves, okay? Now, let's look at Faraday's law of electromagnetic induction. Okay, again, Faraday's law of electromagnetic induction. When a magnetic field varies and a conductor moves near it, then an electromotive force EMF is induced into the conductor. This is called Faraday's law of electromagnetic induction. So if we have a magnetic field and we move a conductor backward and forward within that magnetic field, we can induce an EMF into that conductor. That is what we're saying here, okay? Basically. A galvanometer is a current sensitive meter, and here we have a non-metallic former, and we have a magnet north and south, and we're pushing the north and south into the coil, and here we can see that an induced EMF is being induced, and that's just pushing it in and out with your hands, basically, okay? When the magnet moves towards the coil, which is the current carrying conductor, the magnetic flux moves across the conductors, and an EMF is induced in the conductors of the coil, and the galvanometer moves, showing you that there is a current moving within the coil. A voltage will have to exist, okay, but at least as we're only looking at the coil movement and the current flow in the conductor, the voltage will exist by the pure fact that a current is being moved. Okay, now sometimes you can try to put this in a simpler term, but you have to find your own way of looking at it again in regards to your own style of learning. That is important, okay? Do some groundwork, look at Faraday's law of electromagnetic induction, see what it says, see if you can apply it for yourself in a different way, that you become more comprehensible in it. And continuing with Faraday's law of electromagnetic induction, here we have the coil, the magnet now being pushed out, backward, again forward. If the magnet were to move in the opposite direction, then the needle would deflect in the opposite direction as well, okay? The EMF. The strength of the induced EMF depends on three things. If the magnetic field were increased in size, the induced EMF would increase. If the number of turns were increased, then the induced EMF would be larger. If the speed of movement increased, the induced EMF would increase. E equals BLV, where E equals the induced EMF in volts, V equals the magnetic flux density T, L equals the length in meters, and V equals velocity in meters per second. Okay? Now changing magnetic fields around a conductor. Let me just see if I can. Okay, just need to move that around, just make sure that it was inside. Bear with me for a second. Yes, okay, I can go with that. Okay, changing magnetic fields around a conductor. As an AC supply is changing, the current is changing, and so is the magnetic field around the conductor. Okay, if a conductor was connected to an AC supply, it would have a positive and negative half cycle. This would mean the supply was changing and the current changing with it. If the current is changing, so is the magnetic field. This changing magnetic field produces or induces a second supply in the conductor. This second induced EMF is said to oppose the supply. It is often called the back EMF. Okay. So what you have here in regards to the back EMF is that you got your AC supply going through your conductor wrapped around a former. I call it a former. Okay. And because you have a supply going around creating a magnetic field, that magnetic field then creates an opposition to that supply. So you then have an opposing force, equal but opposite opposing force in regards to the supply of the conductor. If there is an induced EMF, there is an induced current. This is called self-induction. Okay. And here you will see it here on the diagram. Okay. Again, remember you need to look at this in respect of the relevant video. Fusing. Here we have a diagram simply showing live 5-amp fuse with a switch operating a solenoid, which brings in a contactor to operate something else or whatever. When the coil is unwound, it is just a length of wire. Okay, and all we're showing you here is that the solenoid is actually just a length of wire wrapped around a former that creates a solenoid. The current opposing the supply current reduces the overall current to a value that cannot cause a fuse to operate. Okay, yeah, I think we can go with that. Again, make sure you look at it from your perspective and that you are actually taking and making your notes. Do some additional groundwork and do not just take it off the screen. Changing magnetic fields. Changing magnetic fields produce an induced EMF. They can be caused by the supply or any varying magnetic field near the conductor The strength of the effect depends on the number of turns in the coil, the magnetic flux, the current in current carrying conductor, that's the coil, okay? And when it says here the current, we look at the current in the current carrying conductor, so we're looking at the current in the copper conductor around the coil. The time taken to change, the unit of induction is the Henry, the symbol is L. Now here we are looking at mutual induction. Mutual induction takes place when two coils are brought close to each other, one of which has a current flowing through it. Now, mutual induction you get with a transformer, okay? And here you have the flux linking both coils, and here we have a diagram showing you this, okay? Now, the definition of mutual induction is an EMF mutually induced in one coil only when the current is changing in the other coil, not charging, changing, okay? So that's an error there, okay? Changing, okay? C-H-A-N-G-I-N-G, that should be N. Can I change that? Can I? C-H-A-N-N-N, give me an N. This is my N. When the current is changing in the other coil, okay? Yeah, I think I got that. Can go with that. Yes. I can see. No, leave it for now. Okay. Because there is a current flowing through the coil, there must be a magnetic field surrounding it. This magnetic field interacts with the second coil and induces an EMF into it. Okay? Again, as my previous video said, if we have so much magnetic effect, how can we make that work for us in an electromagnetic force field, or to the idea of gravitational levitation? But maybe those things exist already, we just don't know it as yet. This is mutual induction. This induced EMF produces a very high voltage. Now this mutual induction, this reminds me of a car ignition system. When the breakers open, you get a high voltage induced which goes across the spark plugs to fire and ignite the fuel in the cylinder. This induced EMF produces a very high voltage. This is used in car ignition coils. So I was talking the right stuff. Where the DC from the battery is fed to a coil located within a second coil. Okay. The supply of the first coil is interrupted by a contact which breaks the DC to produce a varying DC. This varying DC produces a magnetic field around the first coil, which then links with the second coil. Okay? Inducing a magnetic effect, and remember the spark between these 2 points here can anything be up to 25 or 30,000 volts. Okay? It gives you a kick if you touch it at the wrong moment in time. I know, I felt it. But that's when I was a young man and could take a lot of little shocks. See, when you're young, you see, you think you're invincible, you see. But believe me, we are not. Lenz's law. I repeat, Lenz's law. The EMF in a conductor or coil acts to circulate current in a direction that opposes the change of magnetic flux that gave rise to the induced EMF. This means whatever caused the change is to be opposed. So you have an opposition to the flow of current within the circuit. Fleming's right-hand rule. And Fleming's right-hand rule. Now I try to get this the right way around, and it should be about right actually, I think, about right there. So, yeah, something like that. Okay, but yeah, but you try that for yourself and see if you can implement Fleming's right-hand rule. Now, one way of determining in which direction current flows is Fleming's right-hand rule. Second finger current, first finger flux, and motion is the thumb. Okay, and I'm trying, yeah, I think I've got it about, or am I? Yeah, just about I think, something like that. But good job we have a diagram, okay? In Fleming's right-hand rule, the first finger always points in the direction of the lines of magnetic flux. This means the finger points from north to south. The second finger points in the direction of the induced current. The thumb points in the direction of the motion of the conductor relative to the magnetic field. So the thumb point in the direction of the motion of, so you'll have a rotation, you can have a rotational motion here of a conductor relative to the magnetic field. Rotating, well, from my perspective, I would look at that as rotating in a magnetic field, basically, for myself. That would just be my little learning note for me, basically, to look at it and keep it in mind. Fleming's right-hand rule continues. Okay, and here you can see the current going away from you. Okay. The conductor is moving from top to bottom. Okay. Magnetic field produced by the induced current. Okay. Now the conductor is moving from top to bottom. As it moves through the magnetic field, the flux flows from north to south. That is your first finger. You already know the direction of the conductor, so your thumb is taken care of. The second finger is left pointing away, and this points to the direction of the induced current. Okay. Well, I hope you found this useful. Okay, and again, please remember to do additional research for yourself so you are up to date with current standards and regulations. and that any amendment or changes to Fleming's right-hand rule, that you are familiar with that. Do some ground research. All you need to do is type it into Google, and that will give you a lot of information. But look at your information in regards to your electrical principles as well, and keep that in mind. Okay, right. Thank you for your time and the day, and I hope that you find this useful. Bye bye.